the Cryospheric Guillotine, an exhaustive analysis of snow cornice hazards, mechanics and risk mitigation in British mountaineering and winter wild camping. 1. Introduction. The architecture of deception. In the high-altitude environment, few phenomena possess the lethal duality of the snow cornice. Visually, they are the crowning aesthetic of the winter ridge, graceful, cantilevered arcs of wind-sculpted snow that define the skyline. Structurally, however, they are malevolent geological traps, static hazards that defy the stability of the bedrock they obscure. Unlike avalanches, which generally require a specific triggering event and slope geometry, a cornice is a ticking time bomb of stored potential energy, capable of catastrophic failure under the weight of a single climber or simply through the vagaries of a shifting temperature gradient. For the British mountaineer, or indeed the winter wild camper, the cornice represents a ubiquitous and particularly insidious threat. The unique meteorological conditions of the British Isles, characterised by the collision of maritime air masses with cold polar fronts, create a snow climate that is exceptionally conducive to the rapid formation of massive, unstable cornices. These are not merely decorative fringes. On the high plateaus of the Cairngorms or the precipitous ridges of Ben Nevis, cornices can extend horizontally for 5, 6 or even 10 metres over the void, masquerading as solid ground to the unwary navigator battling a whiteout. This report serves as a comprehensive operational analysis of the snow cornice hazard. It moves beyond basic awareness to explore the granular physics of formation, the mechanics of failure, and the specific historical context of fatalities in the UK mountains. Furthermore, it provides an exhaustive technical manual on the navigational countermeasures required to survive in this hostile terrain, specifically the dogleg and boxing techniques that form the bedrock of winter mountain safety. 2. The aerodynamics and mechanics of cornice formation. To mitigate the risk of a cornice, one must first understand the invisible forces that construct it. A cornice is not simply a pile of snow, it is a complex aerodynamic structure resulting from the interplay of fluid dynamics, particle physics, and thermodynamic sintering. 2.1. The saltation transport mechanism. The genesis of a cornice lies in the transport of snow by wind. When wind speeds exceed a critical threshold, typically around 5 to 10 meters per second, 11 to 22 miles per hour, snow particles are lifted from the windward slope and entrained in the airflow. This process, known as saltation, sees particles bouncing along the surface, gaining momentum. As this particle-laden airstream encounters a ridge crest, the topography forces a flow separation. The air accelerates over the lip of the ridge and then immediately decelerates in the low-pressure zone on the leeward side. This loss of velocity reduces the air's carrying capacity, causing the suspended snow particles to sediment out of the flow and deposit just past the break of the slope. 2.1.1 The reflux vortex phenomenon. Recent cryospheric research has refined our understanding of this deposition. It is not merely a passive dumping of snow. Instead, a reflux vortex forms in the eddy immediately behind the ridge. This rotating column of air acts as a conveyor belt, capturing snow particles that have blown past the edge and circulating them back toward the cornice face. Impact accretion. Approximately 82% of the particles that build the cornice adhere via direct impact from the saltation layer before reaching the front end of the structure. Backmoving accretion. A critical 4% of particles are recirculated by the vortex or influenced by electrostatic fields, attaching themselves to the underside or face of the cornice, contributing to its outward cantilevered growth. 2.2 Sintering, the glue of the cornice. The structural integrity of a cornice is determined by sintering, the bonding of ice grains. In the UK, this process is accelerated by the maritime climate. Mechanical interlocking, dendritic, star-shaped snow crystals physically interlock, creating an initial felt-like cohesion. 1. Pressure. Melting and regulation. The impact of wind-driven particles generates microscopic frictional heat. Combined with the pressure of the snowpack, this creates a quasi-liquid layer on the crystal surfaces, which instantly refreezes, fusing the grains together. Electrostatic attraction. Research suggests that charged snow particles are attracted by the strong electric field generated above the cornice surface, further enhancing the adhesion of snow at the lip. This rapid sintering allows British cornices to grow aggressively, hanging precariously over gullies and corries. They effectively become cohesive slabs of ice and hard-packed snow, possessing high tensile strength but brittle fracture characteristics. 2.3. The morphology of the trap. A mature cornice consists of 3 distinct zones. The root, the section resting on solid ground. This is the only safe zone, yet its boundary is invisible from the surface. The roll, or roof, the rounded top surface that transitions from the ridge to the overhang. This is the zone of deception. The scarp, the vertical or overhanging face on the leeward side. The danger lies in the fracture line. Contrary to intuition, a cornice does not break at the lip. The fracture line typically propagates through the root zone, meters back from the visible edge, where the tensile stress exerted by the cantilevered mass exceeds the sheer strength of the snowpack anchor. Climber standing on what feels like solid ground, 2 meters back from the edge, may still be standing on the wrong side of the fracture line. 3. The spectrum of danger, collapse and avalanche. The threat profile of a cornice is bimodal, the direct hazard of the fall and the secondary hazard of avalanche initiation. Mechanics of collapse. Cornice failure is a study in stress mechanics. The structure is essentially a cantilever beam of snow. Failure occurs when the bending moment induced by gravity and potentially a climber's weight overcomes the flexural strength of the snow beam. Spontaneous failure. This is most common during rapid thermodynamic shifts. A sharp rise in air temperature, solar radiation, or a rain on snow event introduces liquid water into the snow matrix. This water lubricates grain boundaries and destroys the bonds, sintering, that hold the cornice together while simultaneously adding massive weight. This is why cornices are most volatile in spring or during winter thaw cycles. Human triggering. A human load acts as a point stress. If a climber steps onto the roof of the cornice, their weight creates a localized stress concentration. Given that the cornice is already under massive tension from its own weight, this small addition is often the straw that breaks the camel's back, causing instantaneous, catastrophic shear failure. 3.2. The avalanche trigger. A collapsing cornice is rarely an isolated event. It acts as a massive trigger, effectively a natural bomb, dropping onto the slope below. The leeward slopes beneath cornices are, by definition, loaded with wind-deposited snow, often forming unstable wind slabs. Impact loading. The dynamic load of tons of falling cornice blocks hitting the slope below is sufficient to shatter the weak layers in the snowpack, triggering deep slab avalanches. The double jeopardy. This dynamic creates a dual hazard zone. The ridge walker is at risk of falling, while the climber or skier in the corrie below is at risk of being buried by the avalanche, triggered from above. The reach of a cornice accident is vertical and extensive. It affects the entire mountain face, not just the ridge crest. 3.3. The whiteout multiplier. The physical danger of a cornice is exponentially amplified by the optical phenomenon of the whiteout. In these conditions, diffuse light bounces between the snow surface and the cloud base, eliminating all shadows and contrast. Loss of horizon. The horizon vanishes. The sky and the ground merge into a seamless grey-white void. The invisible edge. In a whiteout, the visual cues that denote the edge of the ridge, rock outcrops, change in texture, disappear. The roll of the cornice becomes indistinguishable from the flat plateau. A walker can cross the fracture line and walk out onto the overhang without any visual warning until gravity takes over. Vestibular disorientation. The lack of visual references can lead to vertigo and the leans, where a navigator believes they are walking straight while actually curving towards the abyss. 4. Catalogue of Catastrophe. Historical Case Studies in the UK. The history of British mountaineering is punctuated by tragedies that serve as grim case studies in cornice failure. These incidents highlight that expertise is no immunity against the physics of the cryosphere. Ben Nevis, the deadliest trap. As the UK's highest mountain, Ben Nevis possesses a summit plateau that is practically designed to entrap the unwary. The plateau is rimmed by the sheer cliffs of the north face on one side and the steep slopes of Five Finger Gully on the other. 4.1.1 The Number 5 Gully Disaster, 2019. In March 2019, the mountain claimed 3 lives in an incident that underscored the link between cornices and avalanches. A party of 4 experienced climbers from France and Switzerland were descending near Number 5 Gully. The triggering event was a cornice collapse. The mechanism, the collapse of the cornice, swept the climbers off their feet and triggered a massive slab avalanche in the gully below. The outcome? The avalanche ran for approximately 600 metres. 3 of the climbers were killed, the sole survivor described being flung down the gully by a torrent of heavy snow. Analysis. This incident highlights the danger of terrain traps. Gullies channel avalanche debris, increasing the depth of burial. Even though the climbers were experienced, the instability of the cornice, likely exacerbated by late-season conditions, proved fatal. 4.1.2 The historic Number 4 Gully Incident. A retrospective account from a mountain rescuer details a tragedy 20 years prior involving a highly skilled climber descending Number 4 Gully. The accident, a slip potentially caused by snow balling up on crampons, led to a fall. The climber fell 700 feet. The rescue effort involved climbing luminaries like Sir Chris Bonington, yet the injuries were unsurvivable. The cornice factor. The account suggests that cornice collapse was a primary or contributing factor. This reinforces the bomb theory. A falling climber may trigger the cornice, or a falling cornice may take the climber. 4.2 Beinn Chaorainn, the navigator's nightmare. If Ben Nevis is the trap of height, Beinn Chaorainn is the trap of geometry. Located in the Central Highlands near Creag Meagaidh, this mountain is infamous for a specific navigational hazard that has claimed multiple lives. The topography. The mountain features a long high ridge with 3 summits. The eastern edge of this ridge is undercut by massive corries, which hold huge cornices throughout the winter. The trap. In poor visibility, a direct compass bearing taken between the south summit, 1,049 metres, and the main summit, 1,052 metres, appears safe on a 2D map. However, in reality, this straight line clips the edge of the plateau. The consequence, walkers following this logical bearing walk directly off the cornice. The edge is often invisible in the mist. There have been several fatal accidents here where parties have simply walked into the void believing they were on the solid ridge spine. This specific hazard has led to the standardization of the dogleg technique discussed in section 8 as a mandatory skill for this mountain. 4.3 Creag Meagaidh, the whiteout disorientation. The sprawling plateau of Creag Meagaidh is complex and featureless in winter, making it a hotbed for disorientation. The 1997 tragedy, a seminal accident occurred involving a leader from the RAF Kinloss Mountain Rescue Team. While leading a training exercise in severe whiteout and gale force winds, the leader walked through a massive cornice near the centre post. 2 other team members fell with him. All 3 were killed in the 1,000-foot fall. Significance. This accident involved professional rescuers with high levels of fitness and equipment. It demonstrated that in a ferocious whiteout, even the most experienced personnel can lose spatial awareness. The Cornice did not discriminate, it simply failed under load. The Teelac near miss. A contrasting story from the same mountain involves a climber and his dog Teelac. In a nighttime blizzard with zero visibility, the dog stopped dead in its tracks, refusing to move. The climber, unable to see, urged the dog on. It turned out they were standing on the lip of a cornice. The dog's instinct saved the party. This anecdote highlights the limitations of human sensory perception in whiteout conditions compared to animal instinct. 4.4 Helvellyn, the English danger. While Scottish mountains are higher, the Lake District's Helvellyn is equally dangerous due to its popularity and accessible ridges like Swirral Edge. The 2010 fatality, a 39-year-old walker fell through a cornice near the summit, landing on Swirral Edge and triggering an avalanche. The lesson: this incident proves that lower mountains are not safer. The freeze-thaw cycles in the Lake District can create extremely unstable, heavy cornices that are just as lethal as their highland counterparts. 4.5 Statistical Overview: Scottish Mountain Rescue. Data from Scottish Mountain Rescue SMR reinforces the prevalence of these hazards. Mountaineering incidents. In 2019, 48% of the 502 total incidents were mountaineering related. Fatality rate: there were 7 mountaineering fatalities in 2019 alone. Common causes: navigation error and lost persons are consistently in the top 5 causes of call-outs. These are the precursors to cornice falls. A lost walker is a walker likely to stray onto a cornice. 5. The art of identification, reading the invisible hazard. Avoiding a cornice requires the ability to identify it, often without being able to see it clearly. This relies on a combination of meteorological deduction and subtle visual cues. Meteorological Forensics, the leeward rule. Cornices form on the leeward downwind side of a ridge, therefore the primary identification tool is the weather forecast history. Prevailing winds. In the UK, the prevailing winds are southwesterly. Consequently, cornices predominantly build on north, northeast and east facing slopes. Wind shift. Analysis. A climber must analyse the wind direction for the 24 to 48 hours prior to their trip. If the wind has been blowing from the north, cornices may have formed on south-facing slopes, which are typically safe. The scouring effect. High winds scour snow from the windward side and deposit it on the lee. If the windward side is stripped back to rock or ice, expect significant loading and cornicing on the opposite side. 5.2 Visual indicators on the ground. When visibility allows, specific signs indicate the presence of a cornice. The roll. On a ridge, if the snow surface curves gently downwards and disappears rather than ending at a defined rocky edge, you are likely looking at the roof of a cornice. Tension cracks. These are the most critical warning sign. A crack running parallel to the ridge edge indicates that the overhanging mass is under tension and is beginning to detach from the ridge. Differentiation: glide cracks versus tension cracks. It is vital to distinguish these. Tension cracks usually appear near the crest of a ridge, indicating a cantilevered block is about to shear off. Glide cracks, glide mouths, occur on slopes, often steep, grassy or smooth rock, where the entire snowpack is sliding downhill due to a lack of friction with the ground. While glide cracks warn of full-depth avalanches, tension cracks on a ridge specifically warn of cornice collapse. Both demand immediate avoidance. 5.3 Probing the perimeter. In conditions where the edge is suspected but not seen and retreat is not an option, a probe can be used, but only with extreme caution and while roped up. The probe check. A mountaineer can probe the snow in front of them. Solid ground feels different from the hollow resistance of a snow bridge over air. However, this is a last resort technique for professional guides or rescue teams, not recreational walkers, as the weight of the person probing can trigger the collapse. 6. Behavioural protocols. What not to do. Survival is often a matter of avoiding specific negative behaviours that increase exposure to risk. Do not trust the edge. The fallacy of the lip. Never assume the edge of the snow is the edge of the mountain. The fracture line is almost always behind the visible lip, in the root zone of the cornice. The peak factor. A common cause of accidents is hikers crawling to the edge to look down. This adds a point load to the most fragile part of the structure. The view is never worth the risk of the structure failing underneath you. 6.2. Do not follow summer paths. The summer line trap. Summer trails often trace the very edge of escarpments to maximise the view. In winter, these paths are buried deep beneath the cornice. Following a GPS track of a summer footpath is a reliable way to walk into the void. Winter lines must be significantly distinct from summer lines, often taking a higher or lower line depending on the terrain, but always further back from the edge. 6.3. Do not linger below. The run-out zone. When traversing corries or gullies, avoid stopping beneath corniced ridges. If you must cross a slope overseen by a cornice, the firing line, do so one at a time, moving quickly and efficiently to minimise the time of exposure. Solar triggering. Be particularly wary during the hottest part of the day, early afternoon, when solar radiation destabilises the cornice anchors. 7. Advanced navigation in hostile terrain. The solutions. When the weather turns and the white room descends, standard navigation is insufficient. Survival depends on micro-navigation, the use of precise bearings, timing and pacing to manoeuvre through terrain without visual references. 7.1. The dogleg technique. This is the standard defensive manoeuvre against the straight line trap, like on Beinn or Chaorainn. It involves deliberately deviating from the direct line to bypass a hazard. The procedure. Identify the hazard zone. You know the direct bearing between summit A and summit B passes too close to the corniced edge. Aim off leg 1. From summit A, calculate a bearing that takes you safely away from the edge, e.g. 45 degrees to the right, into the safe plateau. Measure and pace. Walk this safe bearing for a specific distance, e.g. 500 meters. You must count your paces, double paces, to know exactly when you have covered this distance. Converge, leg 2. Once you have bypassed the danger zone of the cornice, turn onto a new bearing that leads you back to summit B. The equilateral triangle variation, the 60-degree rule. For shorter obstacles, a geometric trick simplifies the math. Turn 60 degrees away from your track, walk for X minutes per pace. Turn 60 degrees back toward your original track. You are now moving parallel to it. Walk until past the hazard. Turn 60 degrees back toward the original line. Walk for X minutes per pace. Turn 60 degrees onto your original heading. You are now back on track. The boxing technique. Boxing is used to skirt a specific obstacle, like a rocky step or a suspected cornice slump, while maintaining the exact original line of travel. Step-by-step execution. Stop at the edge of the hazard, turn 90 degrees right, walk a set distance, e.g. 100 paces, count them strictly, turn 90 degrees left back to your original bearing. You are now walking parallel to your original line, 100 paces displaced. Walk past the hazard. Measure this distance so you know your forward progress. Turn 90 degrees left. Walk the exact same distance as in step 3, 100 paces. Turn 90 degrees right. You are now back on your original line, having boxed around the danger. 7.4. The Ben Nevis summit bearings, a life-saving protocol. Navigating off the summit of Ben Nevis in a whiteout is the ultimate test of a mountaineer's skills. A mistake of just a few degrees can send a walker over the 2,000-foot drops of the north face or into the avalanche-prone Five-Finger Gully. Because of this, every winter mountaineer in the UK must memorise the sequence known as the Harvey or abacus bearings 28. This is a precise dogleg manoeuvre designed specifically to skirt the top of Gardyloo Gully. The protocol consists of two critical legs. First, starting from the summit cairn, take a grid bearing of 231 degrees. You must pace this for exactly 150 metres. This specific heading is vital to avoid the dangerous edge of Gardyloo Gully. Second, once you have completed your pacing, turn to a grid bearing of 282 degrees. Continue on this heading until you are entirely clear of the hazards. This second leg turns you down the zigzag path and keeps you safely away from Five Finger Gully. Critical note on bearings. Please remember, these are grid bearings. You must adjust for magnetic variation if the current angle is significant, though currently in the UK, the difference is negligible for this specific manoeuvre. Above all, the distance of 150 metres must be paced with total accuracy. Stopping short puts you in Gardyloo Gully, going too long puts you into the boulder fields. 7.4. Pacing and timing, the tools of precision. In a whiteout, depth perception is non-existent. 100 metres can look like 10 metres. Pacing. You must know your personal double pace count, how many times your right foot hits the ground in 100 metres. Typical counts are 60 to 65 on flat ground, increasing to 70 to 75 in deep snow or uphill. Timing. Use Naismith's rule, 5 km per hour plus 1 minute per 10 metres ascent, adjusted for conditions. In deep snow and high wind, speed can drop to 1 to 2 km per hour. Trust the watch and the bead counter, never your eyes. 8. Group management and psychology. Surviving Cornice terrain is as much about psychology as it is about compass work. 8.1. The human caterpillar. In severe whiteout, the group should move in close formation to maintain voice contact and morale. However, when probing a route or checking a bearing, the leader can be sent out to the limit of a rope or just to the limit of visibility, while the second verifies the bearing from a stationary position. This leapfrog method ensures the leader doesn't drift. 8.2. Heuristic traps. Confirmation bias. Desperately wanting to be there can make a rock look like a cairn. Social proof. Following tracks in the snow is dangerous. Those tracks might lead to a cornice edge where the previous party stopped and turned around, or worse, fell off. Always navigate your own route. 9. Risk management and rescue protocols. Despite best practices, accidents occur. Preparedness for the aftermath is the final layer of defence. 9.1. The rope dilemma. To rope or not to rope on a ridge traverse. Arguments. Against. If one person falls through a cornice, the rope can drag the entire team into the void unless they are vigilant. Arguments. For. A rope offers the only chance of arresting a fall. Best practice. If roped, the team must move with active rope management. They should stay well down on the windward slope. If a member falls through the cornice, the rope will likely cut deeply into the lip, creating immense friction. The team must immediately drop into self-arrest positions to anchor the fall. 9.2. Avalanche rescue gear. Given that a cornice fall often results in burial standard kit, every member of a winter party, even walkers, should carry an avalanche transceiver, beacon, a probe, and a metal shovel. Search protocol. If a partner falls, the survivors must assess the safety of the edge before approaching. It may be necessary to abseil down or find a safe descent route to the debris field. The search follows the standard sequence: signal search, course search, fine search, pinpoint, probe, strategic shoveling. 9.3. Self-rescue. If you fall, fight. Attempt to self-arrest immediately on the slope below the cornice if it is snow. Swim. If caught in the avalanche, fight to stay on the surface. Swimming motion. Air pocket. As the snow slows, cup hands over the face to create an air pocket before the debris sets like concrete. 10. Conclusion. The British winter mountains are a unique arena where beauty masks brutality. The snow cornice is the embodiment of this paradox. It is a feature of fluid dynamics and thermodynamics that creates a fatal illusion of solidity. The lessons from the tragedies on Ben Nevis, Beinn, Chaorainn and Creag Meagaidh are written in the snow. They teach us that the cornice respects neither experience nor strength. It yields only to the laws of physics. For the mountaineer, the best solution is a layered defence, strategic avoidance, using weather forecasts to predict and avoid leeward edges. Tactical navigation, employing doglegs and boxing to maintain a geometric safety margin. Visual discipline, distrusting the edge and recognising the signs of tension. Preparedness, carrying the tools of rescue and the skills to use them. In the whiteout, when the world dissolves into grey, the map and compass are not just tools, they are lifelines. Trusting the bearing over the senses and respecting the invisible line of the fracture is the only way to walk the fine line between the summit and the void. Thank you.